Let's discuss a question, a link data question from thermodynamics. So basically a polytropic process is given, and so if you plot a polytropic process, it's basically a piston device and the air is compressed. So the polytropic compression is given and it will be something like this. It's not linear, though the curve suggests here. This is state 1, this is state 2, and this is governed by PV power n is equal to constant. Now P1 is given as 110 kPa, T1 is 25 degrees Celsius, and volume is also given at the start, which is 100 liters, that is 100 into 10 power minus 3 meter cube. 1 meter cube is 1000 liters, so that fact is used here. After compression, the final pressure is given as P2, which is 800 kPa, and the temperature is given as 200 degrees Celsius. Okay, so this is the data. Now assume that there is a heat transfer with the ambient 25 degrees Celsius and air behaves as an ideal gas. So that's the basic thing given. Now the work done by air. Now obviously work done by the system will be negative because it's compression, but let's just calculate. Work done by air is given as, work done by the system is given as integral PdV, and we have the fact that Pvn is equal to constant. So if you use these fact here and the formula, I mean using this law, when you integrate PdV after some bit of math, the final thing which you get is P1 V1 minus P2 V2 by n minus 1. So n is your polytropic constant. That's what is this exponent, polytropic, not the constant, the polytropic exponent. Okay, P1 V1 minus P2 V2. So now we need to get a couple of things here, but it is given that it's ideal gas, so PV can be written as MRT. So using that fact, I can write P1 V1 as MRT1 minus MRT2 by n minus 1. Okay, and that can be written as MRT1 minus T2 by n minus 1. Now MR is something which I don't know, so I can use this equation at either of these, either of the start point or the end point. So MR can be written as P1 V1 by T1, because I know all the three values P1 V1 T1 at the start. So MR can be written as P1 V1 by T1, so which is all known. T1 and T2 is all known, and so what is left is n minus 1. So n is your polytropic exponent, which I don't know. So before coming to this work done, I need to know n. Now how do I know n here? Now I know pressure, I know temperature at both the start and the end point. So let's use this governing equation. P1 is constant. Now for V, we can use this ideal gas equation at any time during the process. So it is T by P with some constant Mr whole power n is equal to constant. So this basically means T power n by P power n minus 1 is constant, and which basically means T2 by T1 is P2 by P1 whole power. I can put all the n's together on one side, so n minus 1 by n. I know T2 by T, I know individuals T1, T2, P1, P2. If I substitute that, I'll get, let's substitute here. 298 is the temperature. Let's substitute in Kelvin. So 298 is the the various ways of doing it. Let's see the values and let's substitute it here. So the starting temperature, the T2 is 200 plus 273, which is 473 by 298, which is 25. So 298 is equal to, the pressure P2 is 800 kPa by 100 kPa whole power n minus 1 by n. So from this data one can easily get the n, and from this, like if we calculate from the calculator, this is 7 power n minus 1, and you take the log, and so this is easy. You can just calculate. So n we got as 1.3. If I substitute n here, So only the n is what we don't know. So if I substitute that, so let's see what value I get. So the pressure is 110 kPa. Okay, remember that it's 110 kPa, it's not, so this is 110, not the 100, so sorry about that. So this is 110 kPa, so 110 kPa, it's already into 10 power 3. So let's calculate it here, this formula. Let's do the final math here. So it is 110 kPa into 10 power, let me just do the final work done calculation here. 110 kPa into 10 power 3, and the volume already it's 100 liters, so 100 into 10 power minus 3 in meter cube by T1, which is 298, into the temperature difference. The temperature difference can be written as 298 minus the 473 in Kelvin by N is 1.3 minus 1, which is 0.3. So this is what you get it, and when you calculate, you get minus 21.5 into 1000, which is kilojoules. So minus 21.5, it is negative because it's compression. Externally work is done on the system, so work done by the system is negative. That's why it comes out from the formula. So this formula is work done by the system or work done by air here, minus 21.5. So the answer for this 54th, let's go to the options, is minus 21.5. Answer is D for part A, that is 54. Thank you.